Hello and welcome to our new unit. We're in a new chapter, Chapter 2, Reasoning and Proofs. We're going to start off with 2.2. We're going to skip 2.1 altogether, Inductive Reasoning and Conjectures. So if you want to pause it, we can jump into it. Here's the title, and let's get into it. Start off with Inductive Reasoning and a proper definition. Inductive Reasoning is reasoning that uses a number of examples. Get this out of there. There you go. Ooh, that's terrible. Of examples to arrive to a conclusion. All right. So for example, if we wanted to use inductive reasoning for a problem, one would look like this. What are the next three numbers in the sequence? Three numbers in the sequence. Okay? And we could have, for instance, the numbers 1, 4, 9, 16, 25, ... Now, there are a number of ways to do this. For instance, if we realize all of these are perfect squares, you could say this is 1 squared, 2 squared, 3 squared, 4 squared, 5 squared. So the next number would be 6 squared, which is 36, 7 squared, which would be 49, and then 8 squared, which is 64. So that is using inductive reasoning to come up with the next three in the sequence. We're looking for some kind of pattern, right? Pattern recognition. But there's another pattern that actually happens. I'm going to do this in blue, so just so it kind of differentiates it. If you notice, from one number to the next, it's a plus an odd, the next odd, plus the next odd, plus the next odd, plus the next odd. And you could repeat that pattern if you're using plus the next odd number. Oops, there you go. So there's more than one way to answer it using inductive reasoning, and they could both be correct, which is completely valid. Okay, a conjecture is a concluding statement reached by inductive reasoning. Inductive reasoning. Okay? So, for example, if we're given B is the midpoint of AC, segment AC, our conjecture we could ultimately conclude, or as a result of, that we could say AB is going to be congruent to BC. That is a conjecture. It's a result of that particular given statement. Okay? We also need to come up with, we also have to consider counterexamples, because if something's not true, we need to be able to show it or prove it, and usually we do that with some kind of counterexample. It is one example. You only need one to prove something wrong. One example that proves a conjecture false. Oops, that looks like an M. Conjecture false. So, whenever we break down a statement, we always have some kind of hypothesis and conclusion. Okay, so here we could say, for instance, all people who live in Illinois live in Chicago. And we know that this is false because we could take any suburb from Chicago and say they don't live in Chicago, right? So here's your hypothesis. Hypothesis. And then here's your conclusion. Okay, and we're proving the conclusion false. Okay, we're only going to consider this part of the statement and prove that false. So, a counterexample would be people that live in Schaumburg. That is a counterexample because the hypothesis is still true. Schaumburg is still in Illinois, so the hypothesis is still true. These are people that live in Illinois, but not in Chicago. Okay, so I should say in Illinois, but not in Chicago. Okay, the hypothesis, like I said, in any counterexample, hypothesis stays true. But you prove the conclusion false. Okay? All right. And then we just have some just small things that we have. For instance, we have a lot of statements when we're talking about proofs and conjectures. Statements. It's just a sentence that is true or false. That is true or false. And we use the letters P and Q typically. So I'm going to put P and Q is for the notation. We also need to talk about truth value. Is something true or is something false? Truth value. It's whether a statement is true or false. Is true or false. So we could have statements that we determine are true or false. We say the truth value to this statement is true, or the statement to this truth value is false. For instance, here in this last example, here's our statement. We proved it to be false. The truth value is false because we had a counterexample to it. Okay, and the last one is called a negation. We use the symbol. It looks like a squiggly. It's a tilde. And this just means the opposite meaning. The opposite meaning and it's the opposite meaning and opposite of to the truth or the false, if it's true or false, whether it's true or false. Whether true or false. Okay, and this is I want you to write this underneath it. You often use the word not when we're talking about negations. Okay, so for instance, a quick example just to wrap this up. Our statement P, math is fun. Obviously, this is a true statement. Truth value. 100% true. Then not P with tilde P is not P, or the negation of P. Math is not fun. And that's where you just change the statement. Math is not fun. And the truth value changes. Truth value changes. This is now false. Because our original statement had a true truth value, the negation has to have the opposite truth value. Okay? So here are the tools we need to start with inductive reasoning. If you do have any questions, please ask, and we'll go over a whole bunch of examples. And I'll see you in the next one. Bye.